All right, while you're finding lesson 12, couple of reminders. Okay, first off, tomorrow is Tuesday. I know that sucks because today is Monday, but tomorrow's Tuesday, okay, which means you have a quiz. I will post tomorrow's quiz at the end of the day today. It will be on solubility and naming. All right, so you'll have to use your solubility chart to decide whether something is soluble in water or not, like we looked at there before the break. So you're going to want to review that, okay? As well as your naming stuff. Hopefully everyone finished up their naming sheets over the break, okay? If you didn't, you might want to have a look at that tonight as well. The other reminder has to do with your compounds lab reports, okay? The lab that we did, what was it, Wednesday of the week before our break there, okay? That is due on Wednesday. Remember that if you have that done and you'd like me to look it over, that can happen today in scheduled help, okay, tomorrow in scheduled help, tomorrow at lunch, probably even today in, like, let's say the first half of lunch, okay, I'd be available to look at it then as well, okay, so you got kind of 4 opportunities there to have me look them over if you want some feedback before you submit it on Wednesday before the start of class. Okay, questions on that? Okay, remember that if you weren't here or you lost your data, okay, the data is posted there in Google Classroom. Okay, it's one of the files that's included along with the assignment. Okay, you can get everything you need from there. All right, today we're going to start talking about writing chemical equations, chemical reactions. Okay, essentially, this is the kind of big daddy of the units. Okay, we spend, well, probably a good week and a half, okay, looking at how reactions work, right, so that we're able to write those reactions correctly, because if you can't do that, Chem 20 will be next to impossible for you. All right, so it's pretty important that we are able to do this. Now, we have to be able to write formulas correctly to do this. We got to be able to read names correctly, okay, in order to write reactions, which is why we've said that those are so important as well. So we're going to review the signs of a chemical change. Okay, we're going to learn the types of chemical reactions. We're only going to go over the basic 5. There are actually more than that, but we're going to go over the basic 5. Okay, understand how to identify each reaction type. They are all each obviously different. Okay, and then obviously learn how to write them. Now, if there's a chemical change going on, what are some signs we might see that are evidence that a chemical change has occurred? There could be a temperature change. Okay, what else? Color change. What do we say sometimes forms when I mix 2 things together? We talked about in the solubility. Starts with P. Nobody remembers the word precipitate? Okay, you get a precipitate formed, a solid could form. Okay, there's any number of signs that a chemical change has occurred. The big difference, guys, between a chemical change and a physical change is that whatever I have at the end of a chemical change is different than what I had at the beginning. All right, in a physical change, like let's say the melting of ice, have I chemically changed water? No. Okay, I've changed its state. It went from a solid to a liquid, but it's still 2 H's and 1 O. All right, it is still water. I haven't done anything chemically to it. However, if I burn firewood, okay, that's a reaction between the wood and the oxygen in the air, and when I'm done, I have carbon dioxide and water vapor and whatever soot is left behind. Okay, is that chemically different than what I started with? Yeah, I started with wood and oxygen. That's a lot different than carbon dioxide, water, and soot. All right, can I get the firewood back? No. Okay, and most reactions, guys, are essentially impossible to reverse. Some reactions you can reverse, okay, but it requires usually that you put in a bunch of energy and things like that, and it just doesn't work very well. Okay, so your products of a chemical reaction are chemically different than your reactants. That is what's involved in a chemical reaction. Okay, you start out with reactants, okay, and you go to products. Okay, so you would have something like this. Okay, A plus B gives you C plus D. Okay, things are chemically different on the other side. All right, these are your reactants right here. Okay, these are your products on this side. Okay, just so you know the terminology of reactants and products, because we're going to use those terms all the time when we're talking about chemical reactions. Okay, questions so far? All right. Okay, so in a chemical reaction, like we said, the final products are chemically different from the starting reactants. Okay, evidence of a chemical change, color change, okay, state change. We talked about possibly a precipitate being formed, energy change, that would include temperature change, right? This is one we missed. Odor change. If before the reaction there was no smell, but after the reaction there is a smell, what did you produce in the reaction? Gas, yeah. Okay, a smell, a definitive change in smell during a reaction usually indicates that you've produced a gas. Now, not all gases have a smell. All right, you can produce a gas and not have an odor change. Okay, but it is possible. And most of the time, when one is produced, you do notice either bubbles, okay, or an odor. One of the two. Everyone follow me there? Okay, because you don't get bubbles unless you've got a gas being formed. So when you mix vinegar and baking soda, for example, it bubbles and fizzes like crazy. You're producing lots and lots of carbon dioxide gas. Okay. All right, so could that be a multiple choice kind of question? Okay, talking about maybe the differences between a physical change and a chemical change, okay, or the signs of each. Okay, that would certainly be something we would want to know. Okay. Possibly late this week, okay, but probably next week we will do a lab on chemical reactions, and we'll be looking for, okay, these signs each time we mix new materials together, okay, and essentially that's all this lab will be, is there will be like 8 different pairs of things, and you're just gonna, okay, mix them together and see what happens. Nothing blows up, sorry, okay, but there is some cool stuff that does go on. Right. All right, so we're going to go over the 5 kinds of reactions here. The first kind of reaction, okay, that we'll go over is essentially the simplest one. Okay, we call it a synthesis reaction because we take 2 small parts and put them together to make one compound. All right, most of the time those 2 small parts are elements, but occasionally a synthesis reaction could be a compound in an element or 2 compounds, as long as when they're put together they only make one thing. Okay, that's a synthesis reaction. You will only ever have one product in a synthesis reaction. 99% of the time, synthesis reactions will be 2 elements reacting with each other to form a single compound. Okay, okay, so we got to certainly know, okay, kind of the definition or what goes on in a synthesis reaction. Reason for that: as we move along in predicting or in chemical reactions, we're going to have to predict the products of a reaction given only what we started with, only the reactants. Okay, so you have to be able to recognize if you've got a reaction that has an element and an element reacting, that is a synthesis reaction. No other reaction starts that way. Okay, and from there you'll have to kind of put the product together yourself. We're not there yet. This is the first day. Okay, we might be there Friday or Monday. Okay, but we're not there yet. All right, so our example here, we've got, okay, magnesium reacting with oxygen to form magnesium oxide. Okay, what are these little things here? What are they telling us, Jacob? Yeah, they're telling us the state of matter. Most of the time, at least in Science 10, we don't include them. Okay, but just in a absolutely perfect proper reaction, you do write the state of matter. So magnesium is a solid kind of grayish silver metal. Okay, oxygen's obviously a clear odorless gas. Okay, magnesium oxide is kind of a black tarnish like kind of a solid. Okay, so it tells us the state of matter. You're not going to have to include that under most cases. What are these big numbers for? Right. They tell us how many particles of magnesium there are. In this case, not molecules, but atoms, right? Because it's just an element, right? So it only has atoms. All right. So we've got 2 magnesium atoms reacting with how many oxygen? Okay. 1 atom or 1 molecule? Okay. If there's a little 2, that means that they're bonded together. Okay, so that they're actually a what? a molecule. Okay, so this is an oxygen molecule, 2 atoms of oxygen bonded together. Okay, so we've got that there's, what is there, protons in that one, so it's 8. Okay, so we got 8 protons, okay, so there's 8 protons there, okay, and then the number of neutrons, whatever. They're chemically bonded together, right? They're not just floating around separate, okay? If we had 2 separate ones, then we would just have, okay, we would have a big 2 here with no little 2 there. So if you have a little 2, it means that they're actually physically linked, okay, together. Everyone follow me on that one? All right. On your periodic table, flip that open right now. It's a good time to talk about this. On your periodic table, some of your elements are highlighted. Okay, so some of your elements are highlighted on your periodic table. Okay, the reason some of them are highlighted is because some elements will bond with themselves. Okay, any ones that are highlighted in yellow will bond with themselves once, which means you will have a pair of atoms in that molecule. All right, so hydrogen does that. So when hydrogen is alone, that is not in a molecule, not in a compound, it comes as H2. Okay, it's the same with nitrogen, with oxygen, and everything in group 7. Okay, they all come as pairs when they are by themselves. Okay, that's the key. They don't come as a pair if they're bonded to some other element. Okay, if they're in a compound, they could be any number. Right? But when they're by themselves, they always come as a 2. Everyone follow me there? Right? Phosphorus, okay, is highlighted in blue. When phosphorus bonds with itself, it does that as a group of 4. Okay, so when phosphorus is by itself, it comes as P4. Right? And sulfur bonds with itself and comes in groups of 8. Okay, so it comes as S8 whenever it is by itself. Okay, we call those the molecular elements, okay, because they form molecules with themselves. All right, you don't have to memorize them; they're highlighted on your periodic table, and there's a little color code at the top that tells you these ones are pairs, these ones are quads, and okay, and these ones are octuplets or whatever. All right, everyone follow me on that? Just so you're aware, that's what the color code means, and that'll come in handy here as we start talking about reactions. All right, so oxygen is one of those, okay, and then when they go together, okay, we get what kind of a compound, ionic or molecular? It's ionic. Magnesium is a metal, so we've dropped and swapped. 2 plus and 2 minus gives us MgO, okay, and that's how we do it. Okay, same thing here, okay, with potassium reacting with bromine. Okay, remember that bromine is also highlighted in yellow on your periodic table, so it comes as a pair when it's by itself. Okay, when it goes together with potassium, all right, we've got a +1 and a -1, so when we swap and drop, it's just KBr. Now, again, these big numbers here, they tell us that there are 2 potassiums on this side, and there's how many potassiums over here? 2. Okay, how many bromine over here? There's 1 molecule of bromine. How many atoms of bromine are there? 2. How many atoms of bromine over here? 2. This 2 applies to the molecule. There are 2 molecules of KBr. Okay, so that means over here there's 2 atoms of bromine. Over here there's 2 atoms of bromine. Over here there's 2 atoms of potassium. Over here 2 atoms of potassium. Okay, it has to be that way because chemistry is not magic. I cannot magically create more matter than I started with. That's the law of conservation of mass, or law of conservation of matter, whichever way your Science 9 teacher taught it to you. Okay? In the end, they both say the same thing. Matter cannot be created, and it cannot be destroyed. That means in a chemical reaction, I can end up with more or less atoms of anything as a result of the reaction occurring. I have to have the same number in the reactants as I do in the products. That's what the big numbers are for. We use them to balance the equation. Okay? Everyone follow me there? All right, we'll talk more about balancing as we go along. Okay, the opposite of a synthesis reaction is a decomposition reaction. So in a decomposition reaction, we take a compound and we break it down into its elements. Okay, so a decomposition reaction has only one reactant. Okay, because that reactant is going to decompose, okay, or break down into smaller parts. And 99% of the time, that breakdown will be into two elements. Once in a while, you'll get one that breaks down into a compound in an element or something like that. But most of the time, it's just going to break down into its two elements. All right, so the example we have here, water. Liquid water. If you run or you arc electricity through liquid water, it will break the bonds between hydrogen and oxygen and result in the formation of hydrogen gas and oxygen gas. This is how they make rocket fuel. Okay? It's called the electrolysis of water. And you can produce hydrogen gas and oxygen gas, which is what they pump into rockets, okay, in order to make them go. All right. Now, on this side here, in the reactants, okay, so right here, how many hydrogen atoms are there? Okay, there's 2 in each molecule of water. How many molecules of water are there? 2. So how many hydrogen atoms are there in total? 4. Okay, so whenever you see this 2, it means multiply everything in this compound by me. All right, so 2 times 2 is 4. I've got to have 4 hydrogens on this side. Do I have 4 on this side? 2 times 2 is 4. So I'm good. That reaction is balanced. Okay, how many oxygen atoms are there over here? 2, right? There's one in each molecule, and there's 2 molecules. Okay, over here are there 2 atoms of oxygen? Yeah, they're 1 molecule, but there's still 2 atoms. We always got to make sure we got the same number of atoms on both sides of the equation. Okay. All right, another example of a decomposition reaction. We've got nitrogen triiodide here, and it is breaking down into nitrogen gas and iodine liquid. Okay, iodine actually comes as a liquid. Now, if you were doing this reaction, would you need to look at your periodic table to know that N should be a little 2 and I should be a little 2? Okay, are they highlighted on your periodic table? Yeah, okay. They're both yellow on your periodic table. So it's really important that when you're doing reactions, you look and see, do I need to put little numbers or do I need to put big numbers beside these? All right. So on this side here, how many nitrogen do I have? 2. Do I have 2 over here? Yep. Okay. How many iodine here? 6. Do I have 6 over here? Then I'm good. Okay. Everyone follow me on that. Okay, as we go along, you'll kind of get the hang of how to figure out whether this needs a little 2 or it needs a big number. Okay, it only needs a little number if you've swapped and dropped to discover that little number, or it's one of those special elements and they're by themselves. Okay. Okay, questions on decomposition reactions? Okay. All right, combustion reactions. Combustion reactions are always the reaction between something and oxygen gas. Okay? The something that is reacting is what we call a hydrocarbon because it contains hydrogen and carbon. Okay? Hence the name hydrocarbon. So if you look up here, okay, I've got a molecule that contains 3 carbons and 8 hydrogens. And it is reacting with oxygen gas. That's what fire is. Okay, it is a reaction between something flammable and oxygen gas. All right? The products of a combustion reaction are always the same. You never have to figure out what they are. The products are always carbon dioxide and water. Okay, those are always the products of a chemical reaction, or sorry, a combustion reaction. Which is why on a really cold day, okay, you can see liquid water dripping out of the mufflers of cars in front of you at the stoplights. All right? It's because it's so cold that the water vapor in the exhaust system is actually condensing before it leaves, and it drips out the back. Okay? Most of the smoke that you see coming out of the back of a car is actually steam. Okay? Carbon dioxide is clear. You don't usually see it. Okay? But water vapor is more cloudy. All right. In this chemical reaction here, we got C3H8. Anyone know what that stuff is? You'd use it at a barbecue. Nope. Charcoal, yes, you would use it. An old school barbecue, I'm thinking of propane. Yeah, okay, this is propane gas. C3H8 is propane. Okay, so it's reacting with oxygen gas and it's producing carbon dioxide with water. Now, balancing of a combustion reaction is a little bit tricky. There's a few special rules, okay, for balancing a combustion reaction. Okay, if we have an odd number of carbons, we can just go along and balance. Okay, if we have an even number of carbons, we'll cover that rule in a minute. Okay, on this side I've got 3 carbons. So how many do I need over here? 3. Okay, so what I do is I put a big 3 in front of carbon dioxide, and now I have 3 carbons and 3 carbons, so my carbon is good. All right, the next thing I want to balance is hydrogen, because we always balance these alphabetically. Okay, combustion reactions you always balance alphabetically, because if you try and balance oxygen first, you're just going to be in for a world of hurt. Okay, you're going to be constantly erasing what you wrote. All right, so balance it alphabetically. I've got 8 hydrogens over here. Over here, I've got 2. What times 2 gives me 8? 4. So I put a big 4 there. 4 times 2 is 8. So now my carbons are balanced and my hydrogens are balanced. Now I've got to look at my oxygens. 3 times 2 is how many? 6. So I've got 6 oxygens here, and how many over here? 4. Okay, so 6 plus 4 is how many? 10. 5 times 2 is 10. All right, so does that equation work? Got the same number of everything on both sides. 3 carbons, 8 hydrogens, 10 oxygens. Okay, that's kind of how the process of balancing works. We'll go over that a little bit more. Don't worry if you don't get it right now. Okay, so we balance alphabetically always, and then our other rule has to do with if we have an even number of carbons. So once in a while, you will run into, oh, it's all blue. Okay. Okay, once in a while you'll run into this problem. Let's say we're dealing with C6H14. All right, products of a combustion reaction are always what 2 things? No, I got oxygen over here. Products. Products are always water and carbon dioxide. Okay? Water and carbon dioxide are always our products. So CO2 and water. Okay, so here's how you balance. Okay? We call this rule, and this is a special rule, it only applies to combustion reactions. Okay? We call it the rule of 2, because it's the second rule. Okay? If you have an even number of carbons, start with a 2. That's why it's called the rule of 2. Okay? Works every time. Okay? If you have an even number of carbons, you start with a 2. All right. I've got how many carbons here now? 2 times 6 is 12. All right, so I got to go over here and put a 12 there. Now I have 12 carbons on both sides, so my carbon is balanced. Okay, I've got how many hydrogens? 2 times 14 is 28. All right, so I got to go over here. Oh, all right, what times 2 will give me 28? 14. All right, so I put a 14 here. 14 times 2 is 28. All right, I've got 28 hydrogens on both sides. Okay, I've got 12 carbons on both sides. Now I got to look at my oxygens. I don't know how many I have over here, but I know how many I have over here. All right, what's 12 times 2? 24. Okay, and there's 14 more over here. All right, 24 plus 14 should be 38, right? Okay, so I've got 38 oxygens over there. I need to have 38 over here. Well, 19 times 2 is 38. Okay, is my equation balanced? Sometimes you deal with big numbers. Okay, it's not that big a deal. Okay, the reason we had to put this 2 here is if we didn't, we would have got a decimal when we tried to balance the oxygen. Can you have half of a molecule? No. Okay, you can't. Right? So that's the reason we do it that way. All right. Again, don't worry if you're not clear on the balancing yet. It's something we're going to be working on for the next little while. Okay? But just have those rules written down because we're going to come back to those quite often. Okay? Has everyone got the rule of two written down? All right. The last two reactions are what we call replacement reactions. Okay? And they are just like they sound. Something is going to replace something else in the reaction. Replacement reactions always involve ionic compounds. You will never, I repeat, never have a molecular compound in a replacement reaction. Okay? Okay, so in a single replacement reaction, essentially what you have is an ionic compound reacting with an element. That element can be a metal or a non-metal, doesn't make any difference. Okay? What you will have when the reaction is done is an ionic compound and an element. They'll just be different than what you started with. So essentially what goes on is this. You have this guy by himself, and there's this nice couple dancing. This guy thinks she's pretty hot and decides he wants her for himself. So he beats the hell out of this guy and takes off with the girl. And now this guy ends up alone. Okay, so we started out with this person by themselves and these two together. When we're done, different people were together and this person was alone. A new person was alone. All right? Everyone follow me? Now, it's important that we always end up with an ionic compound at the end. We can't have a molecular compound. That means if there's a guy by himself, there has to be a guy by himself over here. Okay? Chemistry is old-fashioned. All right? We can't have two guys dancing together on this side. Okay? Chemistry is old-fashioned and doesn't like that. I'm not saying there's anything wrong with that, but chemistry doesn't like it. Okay? Because that wouldn't be an ionic compound. In an ionic compound, you have to have a metal and a non-metal. In other words, a man and a woman, if we're making an analogy there. Okay? Everyone all right with that? I'm not making any social commentary here. I'm just telling you that chemistry works this way. All right? Okay. Now, what if instead of a metal and an ionic compound, we had a non-metal and an ionic compound? That would be like having a girl over here and a guy and a girl, which means that on this side we have to have a guy and a girl by herself. Okay? Or an ionic compound and a different non-metal by themselves. Okay? Everyone all right with that? Okay? You always have to end up with an ionic compound. Right? Because we said you're never going to have molecular compounds. Okay? We've already said back when we talked about compounds, you never have two metals together, right? Did we ever go over any compounds in the naming that had two metals together? It just doesn't happen, right? Okay? You can have two non-metals together, that's a molecular compound. But since replacement reactions only involve ionic compounds, you can never have them in these kind of reactions. All right, so looking at this reaction here, I've got a metal by itself, copper. And I've got this ionic compound, silver nitrate. Now, this would be a solution. That's what AQ stands for, aqueous, so dissolved in water. Okay, and I would throw a piece of copper in there. In fact, if you run this reaction, okay, like if you throw a penny into a solution of silver nitrate and come back the next day, the penny will be plated in silver. All right, you'll still have the same shape, but it'll be covered in a thin layer of silver metal. All right, and the solution will turn blue, because all compounds that contain copper are blue. Okay? Now, don't think you're going to get rich off of this reaction. Silver nitrate's really expensive because it contains silver. Yeah, okay, and you could do this reaction. So, yeah, silver nitrate's kind of expensive stuff. You're not going to get rich off of throwing pennies. Okay, the alchemists would have loved this reaction, right? Okay, throw pennies into silver nitrate and watch them turn to silver. Yeah, okay, would have been great for that. It's not what they would have thought, okay, but it does actually produce silver. All right, so we would get solid silver on this side and copper nitrate over here. So, copper was the metal by itself in the reactants. Silver's the metal by itself in the products. So we're good there. Okay, here's our starting ionic compound, and here's our ending ionic compound. Different. Okay, copper ends up with nitrate, silver ends up alone. So essentially, what you do is you swap whatever's alone with whatever's like it in the compound. So I have a metal here, I swap it with the metal. If this was a non-metal, I'd swap it with the non-metal. Okay? So it's pretty straightforward. As long as you can tell metals from non-metals, replacement reactions are pretty easy. All right, and we can see that this reaction is, of course, already balanced. Okay, there's one copper over here. There's one copper over here. Okay, how many nitrates are there over here? Well, there's 6 oxygen. How many nitrates are there? 2, right? It's in brackets. Nitrate is in brackets, and the 2 says there's 2 of them. Okay, I go back over here. Do I have 2 nitrates over here? Yeah, it says there's 2 silver nitrate molecules. That means there's 2 nitrate ions. Okay, and there's 2 silver atoms and 2 silver atoms, so we're good. Okay, all right with that. Okay, let's have a look at an example here that contains a non-metal reacting. So let's say we've got so I've got chlorine, which is one of the special nonmetals. Okay, it comes as a pair when it's by itself, reacting with sodium bromide. All right, so who's going to get bumped in this reaction? Sodium or bromine? Bromine. Bromine has to end up alone because it's a nonmetal, and the thing that's alone over here is a nonmetal. So on this side, sodium's going to end up with chlorine, right? Okay, and bromine's going to end up alone. Now, is bromine highlighted on your periodic table? It is. So it comes as a 2. All right. Now I got to swap and drop this one. That's a plus. That's a minus. Okay, so that's good. Now I got to look at balancing this thing. Okay, because right now it's not balanced. I've got 2 chlorine atoms over here, but how many do I have here? Just 1. So what do I have to do? Do I put a 2 here or a 2 there? Big 2 or little 2? Big 2. I can't put a little 2 there. I swapped and dropped to figure out how many of each there was. Okay? So we use these big numbers called coefficients to balance our chemical reactions. All right, so now that gives me my chlorines being balanced, and now I've got how many sodium over here? 2. How many here? Just 1. So what do I need to put here? A 2. Okay, and when I put that 2 there, that gives me how many bromine? 2. Always a good sign. Okay, if your last number makes the last thing work out, you did it right. Okay, now everything is balanced. Right, there's 2 of everything on both sides. All right, so basically you kind of just go back and forth until everything's balanced. Right, you generally start with something that's high in number to start your balancing. All right. The other kind of replacement reaction is double replacement. Okay? In a double replacement reaction, you simply have 2 ionic compounds reacting. And all you're going to do is change the partners. All right? We usually just say swap the metals. Okay? So I've got calcium chloride in this reaction reacting with sodium carbonate. So all I do to make up my new compounds is swap the metals. Sodium ends up with chlorine. Okay? Calcium ends up with carbonate. I've got 2 new ionic compounds on that side. Okay, so if we're using our dance partners analogy again here, this is 2 couples who simply switch partners. Okay? Not like that new A&E show that's coming out that's really awful. Okay? All right, everyone with me there? Yeah? Okay. Now, let's have a look at possibly balancing one of these reactions here. So let's look at okay, so I've got magnesium oxide reacting with lithium fluoride. Okay, on the other side, I need to have 2 ionic compounds, but they got to be different than what I have here. So that means magnesium needs to end up with who? With needs to end up with a non-metal, right? I got to make an ionic compound here. So I want to swap my metals. All right, so magnesium's going to end up with fluorine. Okay, and lithium's going to end up with oxygen. That gives me metal, non-metal, metal, non-metal. Remember, chemistry is old-fashioned. It wants to have ionic compounds. Okay, one of each. Now I got to swap and drop. This is a 2 plus, and this is a minus 1, so I drop and swap. Okay, there's my compound for that one. Okay, this is a plus 1, and this is a minus 2, so when I drop and swap, I get this. Now what do I do? Now I got to balance the whole reaction, because right now I've only got 1 fluorine over here, but I've got 2 over there. Okay, and I can't magically create stuff. So if I got 2 fluorines over here, I'm going to put a 2 right here. Okay, that gives me 2 fluorines on both sides. It also gives me 2 lithium. Is there 2 lithium over here? Yep. Okay. How many oxygen on this side? Just 1, right? There's no number beside it, no number in front of it. Okay. How many over here? 1. Okay, so that's balanced. 1 magnesium, 1 magnesium. So the equation is balanced. Okay, so balancing's not that tough. You just check and make sure everything's got the same number as it has on the other side. All right, questions on that? Okay, that's it. That's the 5 reaction types: synthesis, decomposition, combustion, single and double replacement. Okay. All right, when we write a chemical reaction, okay, there's a few things we have to say. We have to say, here's what I'm putting together, here's what I'm going to get, and here's how much of everything I need. Okay, that's what the big numbers, the coefficients we use to balance, tell. Okay, there's this much of this and this much of that. All right, so in this reaction here, okay, when we're looking at it, I've got how many nitrogen atoms? How many? 3. There's 3 nitrogens on this side. There's how many over here? 2 times 1 is 2, plus 1 more is 3. They don't have to be together as long as there's 3 on both sides. See, that's where it can get tricky. You got to kind of track them all. Okay? All right, on this side there's how many oxygen? 6 plus 1 is 7. Okay, over here 6 plus 7. All right? And there's, for hydrogen, there's 2 over here and there's 2 over there. So it's important to be able to read, okay, a chemical compound and know how many atoms are in that, and then be able to do the multiplication. All right, so that's a balanced chemical reaction, okay, and in a balanced chemical reaction, the total number of each kind of atom in the reactants is equal to that in the products. Okay, important that we know that. Okay, that's the whole purpose of obeying the law of conservation of mass. Okay, and like we said, coefficients are used to balance the equations. That is the big numbers. I cannot change or add the small ones, all right? Because that changes the chemical. Okay, if I change the small numbers, that changes the chemical. I can't do that. Okay, I have to work with what I have. All right, here's what I want you to do. Okay, for these reactions, I want you to identify the type: synthesis, decomposition, combustion, single and double replacement. Okay, I want you to balance it as best you can. Okay, and write it in words. Let's start with just the first 2 for now. Okay, so you're going to write it in words. So essentially it's like naming. That's not too tough. Okay, identify the type, comparing it to your notes, and then try and balance it. All right, try the first 2 for now. I'll give you a few minutes, and then we'll go over them together. And then we'll try a couple more. Okay, let's just have a look at number 1 here first off, and then we'll give you a few more minutes for number 2. Okay, so in number 1, I've got an element reacting with an element to form a single compound. So what's the reaction type for that? That's a synthesis reaction, right? Okay, so we know that we'll just write S, synthesis. All right, now we've got to write out the names of everything. Right, what's this stuff? Nitrogen. Okay, we don't put a dye there, it's still an element, so it's just nitrogen. Okay, and this stuff is just hydrogen. So nitrogen plus hydrogen okay, is giving us this stuff. Ionic or molecular? Molecular. Nitrogen and hydrogen are both nonmetals. Hydrogen's a nonmetal when it's listed second. All right, so this is nitrogen trihydride. Okay, so now I've written it out in words. Now we got to balance it. Okay, what's present in the highest number? Hydrogen's present in the highest number. Okay, there's a 3 on this side and there's a 2 on this side. What's the lowest common denominator of 2 and 3? 6. Yeah, lowest common multiple is 6, right? So if I can make 6 on both sides, I'll have it balanced, because there's no way for me to balance 2 and 3. Okay, so what do I need to multiply the hydrogen on this side by to get 6? 3. Okay, and over here? 2. All right, and when I do that, does that make my nitrogens work out? It does. Okay, always a good sign. Okay, if your last number that you put in makes the last thing balance. Okay, all right, I'll give you a couple more minutes on number 2. Number 2 you should be able to do really easily because it's balanced in your notes previously. All right, for number 2, I've got an element reacting with an ionic compound. What kind of reaction is that? I hear someone whispering, a single replacement. Okay, it's a single replacement reaction. Remember, if it's got an ionic compound in it, it's probably a replacement reaction, especially if it's element plus ionic compound. All right, so we've got a single replacement reaction going on here, so we can write this is SR, for single replacement. Now we got to write it out in words. Cu is copper. Okay, this stuff is silver nitrate. Okay, and that's going to give me silver plus copper nitrate. However, in naming, does copper have more than one possible charge? Okay, so which copper is this, 2 or 1? It's copper 2. Okay, there's 2 nitrates here. Okay, they're a -1, so this means this copper 2 nitrates. Okay, and guys, honestly, I have not had an exam, a unit exam, where I didn't have a couple of these at least, where I just said, here's the reaction. Write it in words, balance it, and give me the type. Okay, I can't remember a time where I did not ask that. Okay. Yes. All right, so now I got to balance it. Now, what thing should I balance first? Because there's a lot of stuff here that I could balance. What should I balance first? Okay, as a general rule, balance whatever is present in the largest number. Okay, unless it's oxygen. We'll get to that. Okay, right now, nitrate is present in the largest number. There's a 2 beside nitrate over here. Everything else is a 1. All right, so I'm going to balance nitrate first. There's 2 nitrates over here, but there's only how many over here? 1. Okay, don't get confused. NO3, that's 1 nitrate. There's 3 oxygens in nitrate. There's only, but this is 1 nitrate here. Agreed? All right, so what do I need to put in front of this? A 2. Okay, there's 2 over here. I need to put 2 over here. I can't put brackets around and put a 2 there. That changes the compound. All right, when I do that, that gives me how many silver now? 2. So I got to go over here and make my silver work by putting a 2 there. The last thing I got to check is copper. There's 1 copper here because there's no number in front. Okay, and there's 1 over here. Is my equation balanced now? Yep, it is. Okay, so we go back and forth. Start with the largest number first. Okay, general rule for balancing. Do oxygen last whenever possible. I don't know why, but oxygen always messes stuff up if you do it early. Okay, don't know why, just that seems to be the way it works out. All right, give you a couple minutes to do 3 and 4 here. Okay, give them a try. Okay, let's have a look at the third one here. So I've got a compound that's not ionic, okay, and it's got carbon and hydrogen in it that's reacting with oxygen. What kind of reaction is that? It's a combustion reaction. The dead giveaway, the products are carbon dioxide and water. Anytime the products are carbon dioxide and water, you're looking at a combustion reaction. Okay, so we can identify that as C, combustion. Now, I've got to write these out with their names. So this is carbon tetrahydride, also known as methane, okay, plus oxygen gives me water. And it's okay to name H2O as water. Don't try and go like dihydrogen oxide or hydrogen monoxide or what. Don't. It just, okay. Plus carbon dioxide. Okay. Now I've got it written in words. Now I need to balance it. We had two rules we had to remember for balancing combustion reactions. The first rule is you balance it in alphabetical order. The second rule is the rule of two, which only applies when you have an even number of carbons. Do I have an even number of carbons here? No, one is an odd number. Okay, so I can just start out alphabetically. There's one carbon over here. How many over here? One. All right, carbon's good. Okay, there's 4 hydrogens over here, and there's 2 over here. So what number do I need to write right here? A 2, right? Okay, so now I've got my 4 hydrogens. Now I've got to make my oxygens work. There are 2 oxygens here, and there are 2 here, which gives me how many in total? 4. So what needs to go here? 2. And we're done. Okay, it's balanced. Taylor? Just with combustion, yes. Okay, we only apply those rules to combustion reactions. Everything else, go with the largest number first. All right, how many people have got the fourth one done? Okay, I'll give you a couple more minutes on the fourth one. All right, so for number 4 here, I've got a compound, and it's breaking down. It's not reacting with anything else. It's just breaking down into 2 smaller parts, which is a it's a decomposition reaction. So we'll just say decomp, all right? And now we've got to balance it all out. Okay, sorry, we got to write it out. Water, okay, goes to hydrogen and oxygen. Okay, now we got to balance it. 2 hydrogens, 2 hydrogens. So far that's okay. Okay, but over here there's 2 oxygens, and over here there's only 1. So I need a 2 in front of this, which now gives me 4 hydrogens. So a 2 here will balance the rest of the reaction. Okay, just starting to make sense? All right, you guys try the last 3. I'll give you a few minutes here, and we'll go over them near the end. All right, let's have a look at the next one here, guys. So in the next one, I've got chlorine as an element reacting with sodium iodide, which is an ionic compound, to form iodine and sodium chloride. So I've got element and ionic compound, which is what kind of reaction? Single replacement, right? Okay, so we got a single replacement reaction. Okay, we got to write everything out name-wise. So we got chlorine, okay, plus sodium iodide, okay, plus sodium chloride. Whoop, sorry, missed one here. Iodine plus sodium chloride. Okay, and now we got to balance. Okay, we said if it's not combustion, we start with the largest number. So that could be chlorine or iodine. Doesn't really matter which one I start with. So I've got 2 chlorines over here, and I've only got 1 over here. So I put a big 2 in front of that, which gives me how many sodium? 2. So I go back over here and balance my sodium, which makes my iodine work out, and we're done. That one's good. Okay. How many people have done the second last one? Okay, so let's have a look at that one too then. Okay, I've got ionic compound reacting with ionic compound, forming 2 new ionic compounds. So it's a double replacement reaction. All right, got to name it. This stuff here is calcium chloride. Okay, this stuff here is sodium carbonate. And that's going to give us calcium carbonate. Okay, remember for the polyatomic ions, we just write their name as it appears in the chart. Okay, plus sodium chloride. All right, now I got to balance it. Looking at this, it looks like sodium or chlorine is present in the largest number. Okay, there's only 1 carbonate here and 1 carbonate here. People get tricked on that because they see the 3. Okay, but there's only 1 carbonate on each side. So I'm going to start with sodium. There's 2 over here, so I need to put a 2 over here, which now gives me 2 chlorine There's 2 chlorine over here, so that's good. There's 1 calcium here, 1 calcium on this side, 1 carbonate, 1 carbonate. We're good. Okay, putting that 1, 2 in there made it all work out. Okay, how many people have done the last one? Okay, give you 1 more minute on the last one before I do it. Alright, so looking at the last one here. Okay, we've got ionic compound reacting with ionic compound to give 2 different ionic compounds. So it's a double replacement, just like the last one. Alright, now there's no little numbers. If there's no little numbers, it's already balanced. Everything's a 1. Okay, so those ones are super easy. Hydrogen chloride, potassium hydroxide, water, and potassium chloride. Okay, that's what we got in that one. All right, have a look tonight on Google Classroom for tomorrow's quiz. Okay, do that quiz tonight so you get 100% tomorrow. Okay, also remember, you can have me look over your lab reports. Okay, either today or tomorrow before they're due.